Hello everyone, it is an honor for me to be here presenting my work titled Linear Hydrodynamic Instabilities Spatial Analysis Procedure Using Spectral Methods. This talk is given by Diego Landinez with the direction of Professor Guillermo Jaramillo. We work in Universidad del Valle, Cali, Colombia. The presentation is organized as follows. 1. Motivation. 2. Introduction. 3. About the instabilities, hydrodynamics, linear theory. 4. Spectral methods and Chebyshev polynomials. 5. Problem formulation. 6. Results. And 7. Conclusions. What is the origin of this work? This work originated from Guillermo Jaramillo's work on the analysis of instabilities in a jet. In his work, Guillermo Jaramillo proposed a procedure to quantify the wavelengths of the instabilities of an incompressible jet flow. These instabilities generate the transition from laminar to turbulent flow in the jet as shown in the figure 1. Figure 2 shows the experimental data of the wavelength of the instabilities shown by the triangular marks obtained by Portillo, and the wavelengths obtained by Guillermo Jaramillo through his proposal are shown with the continuous line. Guillermo Jaramillo, in his proposal, implemented the implicit linearized stability theory that used the Rayleigh equation to characterize the instabilities in the flow in analytic way. Guillermo Jaramillo solved the Rayleigh stability equation using shooting methods, and notice that these methods consume a lot of time in solving the problem. Thus, in the search to improve the numerical efficiency of the Jaramillo method, spectral methods are proposed as a numerical alternative. The linear theory of hydrodynamic instabilities determines the emergence of transition process in the flow. This theory states that if a flow is unstable to a small amplitude perturbation, then the flow will be unstable to larger amplitude perturbations. The linear theory of instabilities initially considers a laminar flow in which certain disturbance of a wave nature arise. The amplitude of this perturbation grows exponentially downstream of the jet, initiating flow turbulence. This theory has been implemented to determine the transition from laminar to turbulent flow in different types of jets. For incompressible flow, as shown in the figure 3, and compressible flow for a small Mach number, as shown in the figure 4. To analyze the instabilities with the implicit linearized stability theory, both the implicit flow and the disturbance that generates the instability must be modeled. A two-dimensional flow is considered that propagates in the streamwave's x-coordinate. Furthermore, the flow will be considered incompressible and implicit. Therefore, the flow will be modeled by the dimensionalist Euler equation in the x direction, as shown in the equation 1. The boundary conditions are those of an external flow in spacewise y-coordinate as shown in equation 2. The horizontal velocity of the flow, as shown in equation 3, is composed of two terms. Capital U is the main velocity profile and U prime is the perturbed component of the velocity. The perturbed component of the velocity is modeled by defining a perturbed stream function C prime, as shown in equation 4. The perturbed stream function is modeled considering the disturbance as plane wave of amplitude phi, wave number alpha, and frequency omega as shown in equation 5. In spatial analysis of hydrodynamic instability, it is considered that the amplitude of the perturbation grows in space, and the growth of the amplitude in time is neglected. Hyperbolic tangent velocity profile, as is shown in the equation 6, is used to model free shear boundary layer flow. The hyperbolic tangent profile approximates the velocity distribution that occurs between the jet and its surrounding. Combining the previously mentioned consideration, the Rayleigh equation is defined. The Rayleigh equation determines the unstable modes of perturbation defined by wave number and frequency. As mentioned previously, the, the spatial analysis of hydrodynamic instabilities is generally performed using shooting numerical methods. In this work, the instability analysis was done using spectral methods. To solve the Rayleigh equation, we implement spectral methods. Spectral methods use a high-order polynomial to interpolate the solution of the differential equation over the entire solution domain. The spectral collocation method divides the solution domain into a spatial point known as collocation point. The solution will be constructed from this point. This method was the one we used to prepare this work. The advantages and disadvantages of using spectral methods are: advantage: fast convergence compared to other numerical methods, and no initial guess is required to find the solution. Disadvantage: normally, spectral methods are more difficult to program and are not efficient for non-smooth domain. It is necessary to know whether the solution function is finite or periodic. If it is periodic, the Fourier series is implemented, but if it is finite in the domain, then an alternative is the Chebyshev polynomial. We implement Chebyshev polynomial because the solution of the Rayleigh equation is finite. In the figure 5, the Chebyshev polynomial of degree 0, first, second, and third are presented. The procedure to find the solution for the spatial analysis of hydrodynamic instabilities using the spectral collocation method was carried out through the following steps. Step 1. Define the Rayleigh equation in the domain of the Chebyshev polynomial. To achieve this, an algebraic transformation was used. This transformation will change the original domain of the Rayleigh equation in the y-coordinate to a new domain where the Chebyshev polynomial are defined by the interval -1 to 1. Step 2. Discretization of the domain at the collocation point using the Gauss-Lobato discretization scheme. Step 3. The solution function phi is represented as an expansion of a truncated Chebyshev series. Step 4. The derivatives of the solution function were calculated using the Chebyshev differential spectral matrix dJk. The elements of this matrix are obtained from the collocation points. The higher order derivatives are determined as power of the Chebyshev differential spectral matrix. Step 5. Substituting the first, second, and third steps into the Rayleigh equation, the problem of solving the differential equation becomes an algebraic problem where matrices of dimension n+1 are operated and is represented by equation 13. Defining the coefficient C0, C1, C2, C3, the equation 13 can be written as equation 14. Equation 14 is a third-order matrix polynomial that defines a nonlinear eigenvalue problem. Step 6. Step 6. The nonlinear eigenvalue problem is solved by the linear complementary matrix method. This method converts the problem into a linear one by changing the variable, but results in an increase in the dimension of the matrices. In this case, the dimension increased to 3 times. Then the problem becomes a generalized linear eigenvalue problem, and a Q-sit algorithm can be used to easily solve this problem. The results obtained with the procedure of this work were compared with the results obtained in the work of Mihalke, who implemented iterative methods or tutor methods to solve the spatial analysis of hydrodynamic instabilities. The first result was the real dispersion relationship for different orders of the Chebyshev interpolation polynomial as shown in the figure 6. The data obtained by Mihalke are also present in the figure 6. Since the behavior of the real component of the wave number with respect to frequency is not linear, it is concluded that the phase velocity at which the disturbance propagates depends on the frequency. Figure 7 shows the error approximation of the real component of the wave number with respect to Mihalke's data as a function of frequency. It can be noted that the error is large for frequency less than 0.15, and that to reduce the error it is necessary to increase the order of the interpolation polynomial. The second result that was obtained was the complete dispersion relationship for different orders of the Chebyshev interpolation polynomial as shown in the figure 8. The data obtained by Mihalke are also present in the figure 8. From complex dispersion relationship, the maximum rate of spatial growth of the instabilities can be obtained. This value defines the frequency of the disturbance where the maximum growth of the amplitude of the instabilities occur. Figure 9 shows the approximation error of the component of the wave number with respect to the data obtained by Mihalke for different orders of the Chebyshev interpolation polynomial. Figure 9 shows how the error is considerable for frequency values less than 0.15. To reduce the error, the order of the interpolation polynomial must be increased. Conclusions. The collocation spectral method using Chebyshev polynomial was implemented for solving the spatial analysis of hydrodynamic instabilities in a shear free flow with the objective of determining the maximum rate of growth of instabilities alpha I. The maximum spatial rate of growth of instability was obtained with a precision in an order of 10 to the power minus 6 with respect to Mihalke reported data. A code was written in Python to perform the spatial analysis of instabilities with the Rayleigh stability equation using the spectral method. The advantage that spectral methods have over shooting numerical methods is that they do not require an initial assumption and their convergence times are faster. Thank you.